So welcome everyone to the MIT Energy Initiative's Fall Colloquium. My name is Bill Green. I'm the director of the MIT Energy Initiative. And this is our biggest talk of the fall, and it's part of our ongoing series, Advancing the Energy Transition. Today, we're going to hear from Joseph DeCarolis from the U.S. Energy Information Administration. He's the leader of that important administration. Maybe I'll just talk for a minute, though, about the MIT Energy Initiative. MIT Energy Initiative is the longest established energy hub at MIT, and we support a lot of the energy research on campus, also quite a lot of the policy research on campus and economic research related to energy. We also run the Energy Minor for the undergraduates and a variety of other educational programs related to energy. With the help from our sponsors, we fund quite a lot of important energy research throughout the campus. In addition, we convene discussions like this one, where we bring in speakers who can address different aspects of the energy transition and ultimately help to convene the conversations that will help to build consensus for solutions so we can work together to try to solve the climate problem. Today's speaker, Dr. DeCarolis, was formerly a professor at North Carolina State University, and I guess probably he'll return there after he leaves the EIA. He's doing his public service now as leading the nation's foremost agency for collecting and distributing high-quality data related to energy, and one of the best data sets in the world. In his own research, he also works a lot on software and modeling methods, since a key part of the energy transition is trying to figure out where we're going and what the options are for the roads ahead. And as I think he'll probably talk about today, that's can be a challenging task, and hence his title, Stay Humble and Prepare for Surprises. No matter what we project in the computer, it's probably not going to go exactly that way. So without further ado, Dr. DeCarolis.
All right. Well, Bill, thanks very much for the introduction. And yes, it's quite an honor to be here. And yes, I did put the bottom line up front right there in the title, that as we think about the energy transition, we do need to stay humble and prepare for surprises. So this talk combines my insights as a longtime energy modeler and academia, as well as my experience as an administrator at the Energy Information Administration. So in this talk, I'm not going to tell you what I think or what EIA thinks is going to happen with regard to the energy transition. Instead, I want to focus a level higher and talk about the models that we rely on to make these projections. So I'm going to start by setting the stage, and we're going to look at some historical data to understand the current state of the transition. And then I want to talk about the practice of modeling. And there's three components to this I want to talk about. One is just the fact that these models are not crystal balls, but they can serve a purpose. And I want to talk about what I think the utility of using these models are. Second, using EIA as an example, I want to talk about some of the developments over the last couple of decades that took us by surprise and how our projections tracked those developments over time. And third is I want to outline some of the efforts we're undertaking in our long-term modeling program to better prepare us for uncertainty about the future, and we want to develop the ability to analyze a wider range of future scenarios. There's a lot of analyses out there that explore different aspects of the energy transition. Whether you're a modeler or not, though, I hope that this talk gives you some perspective on how to interpret some of those studies. Okay, so before I get into all of that, though, I did want to give just a very brief introduction to EIA. We are the statistical and analytic agency within the Department of Energy. So there's 13 principal statistical agencies across the federal government. Again, we're a statistical agency embedded in DOE. Our mission is to collect, analyze, and disseminate independent and impartial energy information for our stakeholders so that they can make better decisions. You see the word independence here a couple times. That's very important to us. So when we publish data or a report, we don't have to seek the formal approval of anyone else in the federal government. And that independence is very important to us because it means that we can focus on doing our work and providing the best information we possibly can. The other thing I wanted to mention is that we're also policy neutral. So we're not in the business of developing policy, advising on policy, but we do analyze policy. Policy is part of the energy system. And so we do want to be in a position to be able to analyze policy. So when I talk about the energy transition or reducing carbon emissions, as administrator, I'm not advocating for any particular position. But again, I'm looking at it from an analytic perspective and what we need to do to understand where the energy system is headed. We do maintain a comprehensive energy statistics program. So by virtue of being a statistical agency, we're vested with the authority by Congress to collect data from the energy industry. And so we do have a comprehensive survey program. Our energy supply survey program represents our largest operational area, and we produce hundreds of reports that rely on that data that we're collecting from the supply side. On the demand side, we have 3 large multi-year consumption surveys that cover commercial buildings, residential homes, as well as the manufacturing sector. I'm going to breeze through these very quickly, but I just want to give you a sense of the comprehensiveness of the data that we collect. So this is just looking at electricity data. It starts with natural resources on the right-hand side, the primary energy. We look at electricity generation in markets, and then ultimately the sale of electricity to end-use customers. We collect a lot of electricity data. Much of it is on an hourly basis, so this is a really high volume of data, and we want to make that data as accessible to the public as we can. So we've developed dashboards. You've probably, if you work with our data, you've probably seen our hourly electric grid monitor. It's been out for a few years, but you can look at generation data by balancing authority. And on the right-hand side, earlier this year, we released the wholesale electricity market portal. So this is data coming from the RTOs, and you can look at the same kind of information, including generation, but also price information coming from the RTOs. We also, again, this is just another example of our petroleum collection program. It's our surveys. Everywhere you see a pink box with an EIA dash number, that's a survey that we have out in the field. So we're covering the whole supply chain. We're looking at movements, prices, sales, and trade of petroleum across the system. We have a similar survey collection system for natural gas. Again, this is just to give you a sense of the data that we collect. We also have a variety of analytic products. We have a short-term energy outlook that we produce monthly. We actually just released the latest one today. And there we use an econometric model to forecast where we see global, US and global energy markets headed over the next 12 to 24 months. The forecast horizon is always through the end of the following year. We also produce the annual energy outlook. There we're looking at U.S. energy supply, consumption, and trade over a 30-year period. And we use a model called the National Energy Modeling System, or NEMS. And I'm going to talk a fair amount about the AEO and the NEMS model in this presentation. We also produce an international energy outlook, has sort of the same covers the same kind of topics, but it's international in scale. And for that, we use a different model. We use something called the World Energy Projection System. We also produce a variety of other reports and analyses. So for example, Today in Energy, we publish a little piece every day that covers some topical issue in energy. And then there's a variety of reports that we produce to respond to Congress or key stakeholders. Okay, I want to talk a little bit about the energy transition, which is really already underway here. So this is looking at U.S. Primary energy consumption going all the way back to 1940. And you've probably seen this graph, or you've heard about elements of this graph. The thing that stands out to me is just this rapid decline in coal over the last 2 decades. But you can also see a rapid rise in natural gas consumption. You can see that renewables, the green line, particularly wind and solar, have been on the rise. If we zoom in on the electricity sector, that's where a lot of these changes are taking place, and you see the same basic pattern. You see that decline in coal-fired generation, the rise in both natural gas-fired generation as well as zero carbon generation. And again, a big portion of that rise in zero carbon is from wind and solar. We can also take a very zoomed-in view of where we are currently. So this is a Sankey diagram. We actually released this just a couple weeks ago, and gives you more details on energy flows. So if you start on the left-hand side, these are sources of primary energy, and as you move to the right-hand side, you're seeing those sources of energy enter the end-use sector. So the Sankey diagram is looking at energy consumption by source and sector. You can see that in the middle we have the transformation of these primary energy sources into both electricity and waste heat. So the thing that we did in this version of the Sankey diagram is for the thermal sources, for the natural gas, coal, and nuclear, you can actually see the split between useful electricity generation and then the portion that goes to waste heat on the bottom here in this black bar. So if you think about it, right, if we grow renewables, there we're assuming a 1-to-1 conversion. So 1 unit of renewable electricity equals 1 unit of primary energy, but we have all these thermal losses from the thermal sources. So if renewables continue to grow, all else equal, we could potentially shrink the amount of primary energy we need to meet our end-use service demands. Now, as you move to the right into the end-use sectors, the way that we draw the boundary on this diagram is it's fuels that are being consumed by demand devices that ultimately meet our end-use service demands. So you have fuels moving to devices like furnaces, heat pumps, vehicles, and being consumed. Obviously, within each of those sectors, there are additional losses associated with conversion, but we kind of draw the boundary before that. One of the things that I like about this diagram is that it strips away a lot of the technology detail that we're often accustomed to thinking about, and we're just focused on the current flow of energy. So if we're thinking about the energy transition and reducing carbon emissions, I mean, the way I see it, there's 3 basic options. They're not mutually exclusive, right? But we can increase carbon-free electricity and fuels, we can decrease final energy demands, or we can do some form of carbon dioxide removal, right? And the question is, this is historical data that we collect. We have high confidence in this, but how do we advance this, right? What will this look like in 2030 and 2050? And that's where energy modeling comes in. So just to get us started in talking about modeling, a lot of people quote George Box, who said all models are wrong, some are useful. I actually like this quote from Paul Krugman. This was in his New York Times blog. He was actually talking about models of the U.S. economy, but it applies universally to all models, including energy models. And what he said is, models are an enormously important tool for clarifying your thought. You don't have to literally believe your model. In fact, you're a fool if you do, to believe that putting together a simplified but complete account of how things work helps you gain a much more sophisticated understanding of the real situation. People who don't use models end up relying on slogans, all of which are wrong some of the time. Okay? So, models, energy systems, they're too complicated for us to develop, at least for me. I can't develop a mental model of the energy system and project that forward, right? We need some way to organize all of this information into a model. Models allow us to build the self-consistent framework that allows us to systematically explore the future decision space. So you can see the schematic diagram here. I tend to think of models as in terms of layers. And this is meant to represent just a generic energy system model. So on the left-hand side, you see model input data. We've got to go out and gather some primary data. There's going to be some intermediate transformations of that data. And then ultimately, there's going to be a final formatted data set that's going to be fed into the model. On the right-hand side, you can see model structure, and it all starts with governing dynamics. What are the dynamics that are actually going to drive decision-making in the model? Are you performing an optimization? Is it a consumer choice model? Is it an agent-based model? Some kind of simulation, system dynamics? You've got to pick some governing dynamics. Below that, you've got to take those governing dynamics and then encode them into a mathematical representation. And then you have to take the mathematical representation and then implement it in code, right? And then ultimately, you run the model, and it pulls the data and the code together. The model gets instantiated, it runs, and then it produces output that we look at and analyze, right? So there's a very systematic approach to the practice of modeling. So at EIA, to do our domestic outlook, we use something called the National Energy Modeling System. And each of the boxes here represent a separate module. So on the left-hand side, you can see these are sources of primary energy. So I showed you all that survey data that we collect. A lot of that survey data is actually being used to populate the input data sets for the model and to calibrate. You can see on the right-hand side a bunch of orange boxes. Those are the end-use sectors. So those three big consumption surveys that I mentioned, they're being used to develop the input data for the end-use sectors. Along the bottom here, we have intermediate transformations, and then along the top, we've got carbon management, macro activity, and then other drivers like international energy and trade and emissions of policy, which of course are going to affect the outcome. And then we need a way to pull all these modules together. So we have an integrating module that basically iterates through all of these modules and finds a price quantity equilibrium between all of these various modules. Okay, so we've got this great model, right? And sophisticated. What are we going to do with it, right? And the first question you might ask is, should we use these models to produce a forecast? And by forecast, what I mean is, should we use the model to make a prediction about a specific quantity in the future? And I think the answer for me to that question is no. We should not do that. And my thinking on this was heavily influenced by this report by Hodges and Dewar. It was published in 1992. They were researchers at RAND, and they were actually focused on military models. They were thinking about everything from models of fuse activation to simulations of theater-level combat, right? And there was a lot of confusion about can we use these models to forecast and so forth? And their point was, if you're using a model to produce a forecast, it ought to come with some kind of a warranty, right? Otherwise, why am I going to trust the forecast or the prediction? Well, how do you produce a warranty? You have to be able to validate the model. You have to be able to take the model, produce some kind of a forecast, compare it against real-world results, and then say, okay, how accurate is it, right? And they said, okay, so if you want to forecast, the model should be validatable. Well, how do you know if your model is validatable? They lay out 4 different conditions here. The first is, it's got to be possible to observe and measure the situation being modeled. It's pretty obvious. Second, the situation being modeled must exhibit a constancy of structure and time. Third, the situation being modeled must exhibit constancy across variations and conditions not specified in the model. And then fourth, you have to collect enough data to make the predictive tests, right? And when you think about long-term models of the energy system, they fail on conditions 2 and 3. The structure of energy markets, they do change over time. And models of the energy system are highly simplified, so they can change across variations that we're not modeling, right? So I would argue that, we can't really validate these models. And so we shouldn't be using them to forecast. The other thing that I've just observed in my time as an energy modeler is because we can't validate these long-term projections, there's really no guideposts there to determine if I add some new complexity to my model, does it actually add value? Does it give me more insight or not, right? And so my observation is a lot of these models have simply gotten more complex over time as people try and analyze many of these issues in more detail. But we don't really know whether that complexity is buying us more insight. When models are used to produce forecasts, the results are generally pretty dismal. So these are just two examples that are drawn from the literature. The one on the left is the U.S. Atomic Energy Commission. This is a forecast from 1962 looking at installed nuclear capacity. The vertical axis is log scale. They were off by an order of magnitude. The one on the right were a set of predictions about what primary energy consumption would be in the year 2000. And every single study overestimated nobody underpredicted what energy consumption would be. And I want you to remember this example because I'm going to show you some results from EIA that exhibit the same basic phenomenon, okay? Oh, computer went to sleep. So yeah, keep this in mind because I'm going to show you EIA results that are going to follow the same basic pattern. We often anchor on what's happening currently, and we're not creative enough about where things might be headed in the future. Okay, so shouldn't really use models these kind of models for forecasting, but what can we use them for? What are they good for? There's still lots of really valuable uses for these models. They can simply be an aid in helping us think and hypothesize about the future of energy. They can help us create a dialogue among different stakeholders on complex issues. I mean, if we're thinking about something like the energy transition and we want to start a dialogue, there has to be some basis for the dialogue, right? So if you have a systematic representation of the energy system that you can advance into the future, we can start to have a debate about the model and what it means and so forth. We can identify key system features and effects, pitfalls and trade-offs, right? That's where a lot of the insight from this modeling work comes from. We can also identify key sources of uncertainty and knowledge gaps. It might turn out that the model is particularly sensitive to assumptions we're making about a specific technology or sector, but maybe we lack the data to feel confident about how we're modeling that piece of the system. And then finally, you can use models to help inform decision strategies. I know there's a bunch of future uncertainty. I don't know what's going to happen, but I can incorporate that uncertainty into my model and help me come up with a path forward. This idea that models should not be used to produce forecasts or precise projections, they should be used for insight, is an idea that's been around a really long time. So I want to give credit to the folks at the Stanford Energy Modeling Forum who were making this point 4 decades ago, right? I also really like the quote at the bottom by Bill Hogan. It's not the individual results of a model that are so important. It's the improved user appreciation of the policy problem that is the greatest contribution to modeling. All right, so I want to talk a little bit about some past surprises. There have been some energy market developments that have taken not just EIA, but many analysts by surprise, and I want to talk through those a little bit. Before I do that, I do want to mention that EIA does produce an AEO retrospective report every 2 years. It compares the results from our reference case against realized outcomes. And it's really just focused on statistical measures, things like percent difference, average percent difference, standard deviation. And it is really useful, but I do find that it's hard to interpret, and it also ignores all the side cases that we run. Every year we run a dozen cases besides the reference case, and it would be nice to incorporate those as well. And this is just a little bit of a brief aside, but this is there's a risk in just relying on statistics. So you might have heard of Anscombe's quartet. This is 4 data sets that were developed by statistician Francis Anscombe in 1973. And all 4 data sets have nearly identical descriptive statistics. So if you calculate the mean and the variance and the correlation, they're basically all the same. But when you plot them, you get what you have on the right. They are totally different. And his point was, we can't just rely on statistical measures. There's value in actually visualizing the data. So that's part of the inspiration for this new tool that we developed at EIA. This is recently been released on GitHub as an open source tool. You can see the link here. You can download and play around with this on your own. I'm going to show you some results using this tool. Just a few things before I actually show you the animations. One is that our data management practices at EIA have changed a lot. So the further back in time you go, those early AEO editions, it can be hard to mine the data because they're in different formats and so forth. In the earliest years of what I'm going to show you here, so far we've only been able to extract the reference case. We're working to include side cases. And then just another note that the model time horizon has expanded. So in the early years, we only ran the AEO through 2030. Then it was 2040. Now we're moving out to 2040. So you'll see the endpoints for the AEO vary depending on the edition. Okay, so with all of that set up, surprise number one was shale oil and gas. There was a lot of technology innovation around horizontal drilling and treatment into shale, and that radically changed oil and gas development. EIA began examining the impacts of shale resources in earnest beginning in about 2008, but our long-term modeling was slow to catch up. If you go back to the early 2010s, we didn't really have sufficient data or modeling capabilities to have the confidence to project exponential growth in the production of oil and gas from shale resources. By 2013, we were starting to get a handle on some of the data. We realized that the traditional relationship between rig count and production was changing, so this drilling productivity report was launched at EIA. And you fast forward today, and now we've got a large database of shale wells. We can analyze how projection will happen over the long term. But it took us a while to get there. So here's the animation. You all are the first ones to see this. I was playing around with the tool myself and created the animation. So it starts in 2005 and then sequentially adds the results from each AEO edition until we get to 2023. That dark line that remains is actual. That is actual. Here we're looking at domestic dry natural gas production in trillion cubic feet, right? And the thing that jumps out at you is in the early years, our projections were just way too flat, right? We did not pick up on all of the production that was about to come from shale. And even if you look at, in doing this, I realized even in 2023, I'm not convinced that the highest scenarios are high enough. Right? And to me, the goal would be, if we're producing this outlook, we should be able to develop a set of cases that ultimately encapsulate what turns out to be the actual, right? If we develop an envelope like this and actual is above or below that, I don't think we're doing a very good job. So in my mind, the goal is to try and capture actual within the envelope of cases that we run. This is the same exact setup, same format, but now this is domestic crude oil production in million barrels per day. And you see the same basic phenomena. It took us several years to really catch. You see those early years in the reference case, they were just very, very flat, right? And every year we recalibrate, so we move up the curve, but then the projections are too flat. Okay? So that's surprise number one. Surprise number two was the rapid deployment of wind and solar. This is one that I often hear about when I talk with folks about renewables and EIA. And I think there were two factors that drove this. One was the capital costs of wind and solar PV really began to decline rapidly in the 2010s. And the problem at EIA was our baseline capital cost data did not keep pace with reality. We just weren't updating the cost data often enough, and our learning rates weren't high enough. So in the reference case, we have something called endogenous technological learning. So every time the installed capacity doubles, a learning rate gets applied and the capital cost comes down a certain percentage, right? And those learning rates were not high enough. Second thing is, we always, at EIA, because we're policy neutral, we focus on existing laws and regulations. So whatever the policy is, whenever it's set to sunset, that's what we encode into the model. So if a production tax credit was set to expire 6 months after we release the AEO, We assume it expires 6 months after we release the AEO forever for the entire projection horizon. And I'll show you some data to indicate that there were a lot of stops in renewable tax credits that caused some problems for us. This is looking at estimated capital cost data for wind, not just from EIA, which is the blue line, but from some other agencies. And you can see that we were systematically high for several years, right? Higher than these other sources. This is the story about the production tax credit. So this is showing annual wind capacity additions. I know there's a lot of detail on here, but all of those labels are like, the production tax credit for wind expires and then it restarts and it expires and it restarts. And wind development is very sensitive to whether that production tax credit is in place, okay? And so again, year after year, we're making the best decision we can about whether, is the production tax credit in effect or not, right? But we've had so many starts and stops over the years that it's affected our projections. So here's what projected wind generation looks like. You can see, again, we're making the updates every year, but it just goes totally flat after the first few years. And it took us a while before those curves actually start to change. And even now, they're still pretty, you can see they still level out. Okay. Just very similar story with solar. You can see that our estimates, again, they were systematically high compared to several sources from about 2010 to 2015. And this is what solar looks like. I mean, we're barely producing any solar generation at all. Now, what's interesting, though, is solar didn't really start to grow rapidly until later. And so we were able to get caught up, I think, with solar earlier on. And you can see just visually, if you look at the range of projections in the later editions of the AEO, I think we're doing a better job of capturing the actual. Okay, whereas wind started to grow rapidly earlier before I think we were really keyed into what was going on. And then this is the final example I want to show. This is energy-related CO2 emissions. CO2 emissions are just a simple mass balance, right? You have a certain amount of fossil fuel consumption, you multiply by an emissions factor, and you can figure out total CO2. Again, you can see in the early years, we were just assuming CO2 emissions were just going to go on, and increase forever. And a lot of that is due to the fact that we assumed that end-use demand was going to grow, coal was going to remain a significant fraction of electricity demand. I already explained how we sort of missed the shale revolution in the early years in our long-term projections. So we didn't know that all that gas was coming. And with all that gas came lower prices, which then pushed coal out of the market. We also, didn't pick up on the rapid growth in renewables over the last decade. And so for all those reasons, we end up with CO2 emissions that are quite high compared to actual. Now, where do we ultimately end up? Who knows, right? And the final thing I want to point out is if you look as it goes from 2022 to 2023, you can see the effects of the Inflation Reduction Act. So that very last light blue, you can see that the curves really did shift down once the IRA was passed. So what's going on here, right? There seems to be a pattern in all of this. So these are my thoughts, okay? First thing is, as a statistical agency, our projections are based on rigorously derived historical data. Again, we're a statistical agency. So we're really looking carefully at the data, but it can take some time to identify the signal through the noise, but yet we're producing projections every year, right? So again, it took time to see what was happening. The other thing is that I think that judgments about model calibration, how we design scenarios and so forth are affected by cognitive heuristics, okay? If you haven't heard of cognitive heuristics before, heuristics are just mental shortcuts that can facilitate problem solving and probability judgments. This literature goes all the way back to Kahneman and Tversky in 1974, but there's two heuristics that I think really matter for energy modeling. One is the availability heuristic, that people assess the probabilities of a future event or outcome on the basis of how easily they can remember past examples or how easily they can envision future possibilities. And when you're focused on the data that you have, that's what's available to you, and you're going to make use of that heuristic. The other is anchoring and adjustment, that people will often start with an initial value and they tend to anchor on it, and even when you get additional information to move you off that anchor, the adjustment off of the anchor is often insufficient. We don't make big enough adjustments once we learn new things. And I think these heuristics can be hard to overcome, particularly in an environment where modelers can be judged for errant projections, right? If I'm going to be wrong, and I get, well, what happened, right? I'd rather be able to say, look, this is the data that I had. This was the best guess I possibly could make at the time. It takes some courage to really say, well, like it really could grow exponentially. Let's run a case that looks like that, okay? And the thing I want to emphasize is at EIA, we're trying to be as transparent as we can. We have nothing to hide. And the things I'm talking about here, these heuristics, this isn't limited to EIA. This is like a universal phenomenon. This is happening with modeling all over the place. And I'm just using EIA work as an example to illustrate. Okay, so what can we do about uncertainty, right? In the process of overhauling our long-term modeling program, I spent a lot of time going back to this National Research Council report that was released in 1992, and they really emphasized the importance of uncertainty, right? That uncertainty is inherent in the nature of models, and we shouldn't just ignore it or eliminate it. We need to find ways, EIA needs to find ways to incorporate the consideration of uncertainty into NEMS explicitly. And the whole report was based around recommendations for EIA to build and run NEMS. So they thought it was very important. I think it's very important. And to me, the question comes down to, how do you illuminate and inform future energy pathways given all of this uncertainty, right? And I think it really depends on the specific question you're trying to ask. There's not like one method that you should always use to assess uncertainty. It really depends on the nature of the question that you're asking. The other thing is that I think it's helpful to break down uncertainty into two categories. There's parametric uncertainty, and that's uncertainty in the input parameters that we put into our models. So I talked about wind and solar capital costs. We have to make some assumption about what those costs are going to be out through 2050, right? That's parametric uncertainty. And we have a lot of tools in the toolbox in order to try and address the effects of parametric uncertainty. We can do scenario analysis, parametric sensitivity analysis. We can do Monte Carlo simulations. There's something called method of Morris that does a random walk in the input parameter space. Stochastic optimization or robust optimization if we're trying to develop a decision strategy. The second category is structural uncertainty, which refers to the imperfect and incomplete nature of the equations describing the system. So you've got this really complex world out there, right? And you're trying to distill that into a computer model. The equations that you come up with to govern that system are going to be highly simplified, right? That's structural uncertainty. And there's also ways we can deal with this, although there's been less of it, I would say, in the literature. But there can be alternative formulations of the model, different equations. There's a technique called modeling to generate alternatives that I could talk more about later on, or just model intercomparison exercises. Again, Stanford Energy Modeling Forum does a great job. They get a bunch of modelers together. The models are different. They focus all the models on the same issue and then see what comes out, right? Like, why are there differences in the outputs across these different models? That's another way to address structural uncertainty. We know that moving forward, the system is already in a period of rapid transition. And when things are changing rapidly, it heightens uncertainty. And I've just got like a laundry list of things, right, that keep me up at night as a modeler. What are the impacts of climate change? How's that going to affect end-use demands? What are the impacts of climate change on infrastructure and renewable resources? How are we going to build out all this infrastructure and develop new supply chains for clean energy technology? I showed you examples with technology innovation. At EIA, we underestimated the role of wind and solar. What's going to happen in the future? What about novel technologies? What about enhanced geothermal, fusion, space-based solar power? I mean, should those be in the model? What if there's a technology breakthrough and we're missing it? Electricity demand growth. There's a lot of talk about AI in data centers. Does that matter at all? Is that going to matter or not? I mean, or are we just going to improve the efficiency of the chips so much that it's not a big deal? Like, I don't know. Again, I've talked about the role of policy. If there's significant changes in infrastructure, what's the impact on people? And then, of course, there are the unknown unknowns. There are the things that I can't conceive of to put on this list, but are probably going to happen, and we're going to be dealing with, right? So the bottom line is we need to find ways to deal with uncertainty. Now, I want to talk a little bit about what we're doing at EIA. This example is specific to EIA. So we developed something called the reference case. I've mentioned this a few times. And people tend to interpret our reference case as though it is a forecast, right? This goes back to AEO 2022. This was before I joined. And you can see on the left-hand side, I think we define it, the way it's defined is exactly right, that it's a baseline for comparison between side cases to explain alternative trends. But on the right-hand side, 70% of the figures that appeared in that AEO show the reference case by itself. So if you're just reading it casually, you're going to think, hey, this looks like a forecast, right? And I think that that's really problematic, right? I think as a modeler, we never want to put a single result or the results from a single run onto a figure. Just think about it mathematically, right? Even if the reference case was our best guess, the probability of realizing a single trajectory for anything through a continuous solution space is going to be 0. In AEO 2023, we really tried to emphasize, again, the range of results across the cases. So this is looking at electricity generation by select technologies. We're still showing the reference case as that black line, but you can now see that there's a gray band around every reference case result, and that shows the range around the reference case. So we're trying to emphasize, hey, there is a range of outcomes here. We don't know for sure what's going to happen. The other thing we did, we're also experimenting with other methods. This is something that we did publish in the AEO. This is looking at energy-related carbon dioxide emissions. And we actually utilized an approach that was published by CAC et al. In 2017, and it was like directed to EIA. They took the AEO and they built these uncertainty cones, and we decided, hey, let's actually build this into the AEO. All right, so what do we do? What do you do here? For a given projection horizon, let's say 5 years into the future, you calculate the difference between AEO projected CO2 emissions and actual CO2 emissions. And then you do that across all previous AEO additions for that projection horizon, right? And then you repeat that for different projection horizons, for 5 years, 10 years, 15 years. So for each projection horizon there, then you've got a set of differences between AEO and actual. And you can use that information to form a distribution. And there's lots of things to test, and you can assume that you can fit it to a Gaussian distribution. In this particular case, we assumed that it was a non-parametric distribution. And so what you do is if you have a distribution for each projection horizon, you can then use that to fit a cone, and then you can apply that cone to the current reference case, and that's what we've done here. So just to orient you, the black line is a reference case. The two gray lines are the highest and lowest emissions cases that we had in the AEO. And then you can see the cones. So the way to think about the dark blue cone is that it captures 50% of the historical projection errors in energy-related CO2 emissions. And then the lighter blue cone captures 95% of the historical projection errors. There's a couple things I really like about this technique. One is that it's very computationally efficient. We don't have to run NEMS hundreds of times because we have all of this data lying around. So that's a really big advantage. The other thing is that it captures whatever bias there is in our projections. It's being captured because we're comparing actual to projection. The thing that's the weakness of this, though, is who's to say that those historical projection errors apply to the future, right? We don't know that. But I still think that there's something useful to be learned from this exercise. Okay, final thing, just very quickly, I wanted to talk about our long-term modeling plans. A couple of years ago, we embarked on a plan to overhaul our long-term models. Before I get into that, I wanted to explain, well, like, what are the goals for our long-term outlooks at EIA? I mean, we want to be able to capture key market dynamics that drive energy-related decision-making. We do want to provide that policy-neutral baseline. We do want to capture uncertainty and capture the fullest range of possible outcomes. And we want to be flexible and nimble. We want to be able to incorporate new model features easily and produce timely analysis. And then finally, we want to make our modeling work transparent and accessible. The little snippet I took here was actually from the Infrastructure Investment and Jobs Act. This is actually directed at EIA. And it's telling us to strive to build a single, consistent, and open source modeling platform. So we're on this two-track approach. Okay, track one is we need to continue to produce the AEO. So we're updating the National Energy Modeling System. One thing we did was we made NEMS open source. So you can now go to GitHub, you can clone the repo. It's available under the Apache 2.0 license. So if you're feeling ambitious and so forth, please have at it, make use of the model. The data is also there as well. It takes some effort to get it all set up, but we are making it available. The other thing, though, is that we've overhauled the modules. So when we release AEO 2025, it's going to be using a version of NEMS that contains 3 new modules. There's going to be a hydrogen market module that's going to represent hydrogen production and pricing. There's a brand new carbon management module that captures whatever CO2s produced across the sectors. It can be captured and then allocated to either beneficial reuse or geologic sequestration. And then we also have a new hydrocarbon supply module, which will improve the representation of upstream oil and gas. And among other things, we're hoping that these updates will allow us to better represent current laws and regulations, including many of the provisions in the IRA. Okay, track 2 is Project Blue Sky, where we've embarked on a plan to develop the next generation energy system model at EIA. And we want it to be modular, the way that NEMS is. We want it to be flexible. We want it to be transparent. It's going to be open source. And we're going to work really hard on documentation so people can understand what we're doing. We want it to be robust so that we can capture uncertainty and that we have insights that are conditioned on that uncertainty. And we've already released a very bare bones prototype. So you can scan the QR code, takes you to that link there. There's a GitHub repo. So if you're a modeler or you're a coder, please take it for a test drive. Let us know what you think. This is very, very early stage, and we're very open to feedback. Anything from coding practices to I don't like this, or you ought to think about doing it in a different way. We want this to be a community effort, so I encourage folks in the audience that are interested to give it a test. Again, we want to maintain this modular structure similar to NEMS. We're hoping that will allow us to test different approaches, like different governing dynamics. We could even vary the level of complexity by module. So if we have an individual module, we can have a very simple version, and then we can add a feature, and we can do that systematically to build up the complexity, where at each step we know when we add some complexity, what does that bias in terms of insight. If it's modular, we can also isolate particular modules and just run a subset of those modules to answer a particular question. We don't necessarily need to run the whole integrated system to answer every question. So I showed you the diagram in the beginning. The idea here is that you can essentially have different governing dynamics, again, within each module, which gives you the flexibility, again, to test different ideas, right? What if decision-making in transportation sector is driven by an agent-based model? What would that do? It's something you can test. I don't want to get into the details, but we've also worked out some different ways that we could solve the integrated model. There's a way that you can solve it as a single optimization problem, where you take the non-optimization based modules through a set of equivalence relations. You can convert them into constraints and an optimization, or you can just use iterative methods to seek convergence the way we do in NEMS. This is what's in the prototype. We've got different ways to solve the model. We've got 3 toy modules to play around with. We've integrated a couple of ways to analyze sensitivity of input parameters, and then we have some standalone features that we want some feedback on as development progresses. Okay, just to wrap up here, parting thoughts. Energy system is highly complex. It's evolving rapidly. It's uncertain. Long-term forecasts, my opinion, bad idea. We shouldn't be producing point estimates. I've tried to demonstrate that there's this built-in conservatism in the models. Remember cognitive heuristics. We all take these mental shortcuts when we're thinking about data and modeling. There's also that wrong of being fear, or that fear of being wrong or being an outlier compared with other modeling groups. And I think the bottom line is we just need to find ways to explore a wider range of possibilities. Kind of step through what we're doing at EIA. And then this is just my plea. You know, despite our best efforts, there are going to be unforeseen surprises. And if you're a student and you're starting to model, or you're an experienced modeler, whatever you do, don't start believing the numbers, right? There's a tendency when you sit in front of the computer and you're watching the shell spit out numbers at you, maybe not in the beginning, but you'll really start to believe those numbers with high precision, and don't fall for it. Always remain skeptical, which brings me to my last point, that we have to remain humble and intellectually honest about what we know about the future. That way we can provide decision makers with an honest assessment of what we think could happen in the future. And then I won't read these quotes, but these come from Daniel Kahneman's book, Thinking Fast and Slow, about uncertainty and judgments about decisions. And I think it applies so well when we're thinking about energy future. So I'll leave it up here and happy to take questions.
So thank you very much. Maybe we'll take questions from the audience, and I would recommend you read these quotes too. Question? Yeah.
Yeah, I want to start with some heartfelt and admiring thanks for EIA work. I rely on it. It's wonderful, and thank you very much.
Thank you. I'll pass that along to our staff.
Okay, so I have a short question and a slightly longer one. The short one is, do you think about, or can you model...
Can you cut the phone?
Oh, sorry. Do you think about, or can you model the political aspects of, local populations deciding they don't want to see wind farms over, within the horizon, and so they oppose them? Is that kind of politics a varying part of your model? Do you include it?
So I'm going to take off the EIA hat and put on the academic modeler hat and say that, sure, I think that's an interesting thing that one could explore, maybe with an agent-based model. I think at EIA that would be a bad idea. I think that would, there'd be all kind of questions about how are you doing this? It would violate policy neutrality. But I think just as a general modeling idea, sure. Why not?
Okay. Because my opinion is that might be the throttle on a lot of our renewables. And so,
Again, it really depends on the question that you're trying to answer. If it's a technical question about, the limits of renewables, you don't really need to do that. But if you're trying to if you're a sociologist or something, you're trying to understand political coalitions and how that could affect, then sure.
Okay. Well, I'll get to my other question, which is, assuming you'll agree that to reach a 2050 net zero, we need to think about great new things, great new opportunities. Mm-hmm. And I think there is such a great opportunity, in front of us, which is remotely harvested zero carbon liquid fuel, mainly ammonia, which mm-hmm. can be, harvested in the Falklands and then shipped to Philadelphia or something. And so my question is that in your models, or will it be in your models, or what will it take to get that considered in your models?
Yeah, that's a good question. I'll just be perfectly frank with you. Right now, we're not capable of modeling a net zero scenario. We're getting closer to that. We don't have an ammonia pathway in NEMS or WEPS right now, but I think we need to add that capability. My view is we want to have as many of those low carbon pathways in the model as possible. Because eventually we are going to be asked to run those kinds of scenarios, right? Someone's going to come to us and say, run net zero, and we need to be prepared. So ammonia is not in there right now, but hopefully will be soon.
Question? Yeah.
Thank you very much. So I'm wondering if you can say something about how you get the data. I see, for example, that there's this 864 or so that has all the generator data. So say that you realize for your model that you want to make, you need some kind of data. Do you go to the government and say, please make a law to tell them to give us the data? Or?
Yeah, good question. So the way that it works is we, as I mentioned, we're vested with the authority to collect data, but we can't just do that on our own. So there's a process. So let's say we collect a lot of electricity data. The 860 or the 860M is one of those surveys. Let's say we decided we want to ask another question. There's some other piece of data we want. The process is we go to the White House Office of Management and Budget, and then we request from them whether we can change the survey. And there's a whole approval process in order to make that approval. There's something called the Paperwork Reduction Act, and they want to make sure that they want to understand what's the public benefit of collecting this additional information, and then what's the burden on industry, and do those things kind of balance out. So that's the process. If we want to set up a new survey, or we just want to modify an existing survey to ask new questions, there's a process we go through with OMB in order to get that approved. And there's notices that go in the Federal Register so that the public can comment and say, hey, that's a great idea, or no, that's a terrible idea. Why would they want to do that? This, you could get this data somewhere else. So there's an opportunity for the public to weigh in on those data collection proposals as well.
Maybe you take one more way in the back there.
Thanks, Alice, for the presentation. I just had a small question. Will the use of energy models for long-term forecasting be made easier as time passes by? Because the fact we have more data to verify the accuracy of the made projections and therefore learn from it. I don't know if the question was clear with the micro.
I'm not sure if I understand. You're saying...
The point I'm making is just that as time passes by, we'll have more data to verify previous projections we have.
Oh, okay, I see, yes.
Therefore,
yes.
do you consider that this will allow us to better rely on long-term forecastings?
So here's the problem that you get stuck in, and it goes back to the Hodges and Dewar, their conditions for their validation. You could go back in time and you can do all the comparison, all the validation you want based on historical data, but the problem is there's no guarantee that it will work well into the future. And it's because of that constancy in structure through time, right? Unfortunately, the system is not just physics-based, it's human behavior, it's societal trends, it's technology innovation. So you could run your model and realize, wow, I got everything right. Like, my model's great. And it could be wrong about everything for the next 2 decades. So there's really, even though we collect more data and we could do, try and do some validation exercises, you kind of get stuck in this place where it doesn't mean that you're going to do well in the future. So more data doesn't necessarily make it better. That said, the kind of exercise we went through where we show the projections against actual, I do think you can learn a lot. I just don't view it as a validation exercise to prove that the model is precise.
All right. Well, thank you again. That was a very fantastic talk.
Thank you.
And I just wanted to put in a shameless plug. MITEI has a podcast, and if you'd like to hear more thoughts, maybe a little bit along the same lines as what you heard from the speaker tonight, there's some really interesting podcasts with MIT faculty, and so you can just use the QR code to get to it. And thank you again. Thank you for your attention, too.